Today's topic is binomial random variables. This has to do with probability, as we've kind of come out of the probability piece. And although we are going to incorporate it into statistics, especially on Monday, let's see what the heck we are talking about. Suppose you have a bag of 5 marbles. 2 of the marbles are blue, and 3 of the marbles are red. So I got 3 red, I got 2 blue. Very good with that? We're going to reach in that bag 4 times. And when we reach in that bag, we're going to select 1 marble at random, and then we're going to put it back. Okay? So it says replacing the marble after each draw. That's important. What is the probability of drawing out exactly 2 red marbles and 2 blue marbles on your 4 attempts? So I want to model this so we can see it, but we want to know 2 blue and 2 red. Okay? Talk to the person next to you. What's the probability of drawing out a blue? What's the probability of drawing out a red? Go ahead, talk. What do you got?
Is it today? Class average is
So, the probability of drawing out a blue is 40%, and the probability of drawing out a red is 60%, because we have 2 out of 5 and 3 out of 5. Everybody good with that? So, in order to figure out the odds of doing it 4 times in a row, what we would have is we would have 0.4 times 0.4 times 0.6 times 0.6. Does that work for you? Now, here's one thing that makes this interesting is that in order to get 2 blue, you wouldn't have to draw 2 blue and then 2 red. There's another possibility, isn't there? Like, for example, I could draw 2 blue and then 2 red. What's another possibility to get 2 blue? Blue, red, blue, red. What else? Red, blue, red, blue. Red, red, blue, blue.
Red, blue, blue, red.
Red, blue, blue, red.
Blue, red, red, blue.
Blue, red, red, blue. You've got them all. How many is there? There's 6. So this can happen 6 different ways. So what this ends up being is 6 times 0.4 squared times 0.6 squared. That ends up being our probability. Now, just so that I can ease everybody's mind, don't you agree that calculating this, that can be kind of a pain in the butt, couldn't it? To try to look every single time how many combinations are there. So I'm going to show you a shorter way to go around that, but hopefully the 0.4 and the 0.6 weren't too tough to come by. Go ahead, type this into your calculator, see if you can come up with the same value that I get.
I tried to rewatch those movies like summer.
True.
Let's not talk about
Did everybody get 0.3456? Okay, good. So that's a real basic example. We're going to show you what happens when you just change things up a little bit, make it a little bit more complicated, or we're going to give you a couple of shortcuts to just make things easier. Okay? Suppose the question was more difficult. Suppose that a bag has 10 marbles. There are 3 that are blue and 7 that are red. 8 times in a row, you desire to reach in the bag, draw out a marble, you then put it back. What's the probability of drawing out exactly 2 of the blue and 6 that are red. Talk to the person next to you. What is the probability of drawing out a blue? What's the probability of drawing out a red? Go. Our probability of drawing out a blue is what? 0.3, and that's going to happen twice, so we're going to square that. And then we're going to draw out a red. What's the probability of drawing out a red? 0.7, because there's 7 marbles that are red out of the 10. And we're going to take that to what power? To the 6th power. We would then have to figure out how many ways that could happen. That's kind of ridiculous, isn't it? Don't you guys agree that that's something that would be really, really challenging to do? And I don't desire to do that. So are you ready to do something that's easier? And we call this the binomial coefficient. We'll talk about what it means to be binomial in form in here in just a second. But the binomial coefficient is this. It is simply what we say is n choose k. So suppose we have n items and we want to choose k items from that. So in this situation, we have 10 items that are in the bag and we're choosing 2 of them. Okay? Or in this situation, actually, we have 8 items and 2 of them need to be red. Okay? 8 items and 2 of them need to be blue. How do we do this? We perform this by the following. It's going to look super complicated. It's not bad at all. Okay? We have n factorial divided by k factorial times n minus k factorial. Does anybody know what the factorial sign means? How do we calculate 5 factorial? 5 times 4 times 3 times 2 times 1. Exactly. Okay? So hopefully this is something you guys talked about once upon a time in math class. If you didn't, it's no big deal. We'll show you the example of 5 choose 3. 5 choose 3. How do we expand that? Well, on the top, we put 5 factorial. And then on the bottom, okay, look what we do. We put just 3 factorial times, what's 5 minus 3? 2. So I put 2 factorial. So in the top, we have 5 times 4 times 3 times 2 times 1. And in the bottom, you have 3 times 2 times 1 times 2 times 1. And because we're multiplying, these things actually simplify pretty easily. Look at what we have. 3 times 2 times 1 cancels with 3 times 2 times 1. So what do you have in the top? 20. What do you have in the bottom?
2.
So that makes 10. So 5 choose 3 is just equal to 10. It's not that difficult to be able to calculate. Let's go up here to try to figure out how many ways it can happen. How many trials do we have? 8. And how many are we choosing to be blue? 2. So we want to calculate that. So in the top, we'll have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. What are we going to have in the bottom? What's your first number going to be? 2. So I got 2 times 1. What's your other number going to be?
6.
6. 6 times 5 times 4 times 3 times 2 times 1. As long as we can write it out, we can see what cancels pretty quickly, can't we? The 6, the 5, the 4, the 3, the 2, and the 1, they all cancel. What do you have at the top? 56. At the bottom, you got 2. So I see that my coefficient is 28. Go ahead and see if you can multiply that out on your calculator.
Oh, you multiply it.
Did everybody get 0.2964? Okay, so for us to be able to have success with this on the test, as well as for us to be able to have success with this next week, we have to get to a point where you do a problem on your own. Now, I modeled these in situations of marbles and bags because that's the easiest way to see it. We want to kind of look at it in terms of real life. So I would like to do the next 2 with you. I'd like you to try the next 1 or 2 then on your own. If we can do that, then you'll be set for Monday, okay? So let's talk about what the binomial probability looks like. Binomial really means this. Binomial means 2 parts. And the 2 parts means that it's either one thing or it's the other. So notice from our bag of marbles, we were choosing either red or blue. There's other things in life that involve binomial probabilities. For example, flipping a coin involves that. Here's another one. How do you like this? I have the GAD65 gene. You know what that is? The GAD65 gene is a gene that's an autoimmune disorder. It passes down through different groups of people. It is more likely to pass down through males than it is to females. But everybody in my family has a certain likelihood of getting it. I have it. That's the gene that causes eventually your immune system to kill off the pancreas cells, your beta cells in your pancreas. They become diabetic. It's just what happens. I have that. Would it be interesting to know what chance people have of contracting a certain gene within their body? You might want to know that if you're planning a family, right? Like if I have 8 kids, because I'm working on the farm, and I forget, you got combines now, you don't need very many people, I get it. Okay. So, what are we going to do? Okay, what is the likelihood that somebody has a certain type of gene? Well, let's look at that situation here. But the way that we define that probability is pretty simple. The probability that x is equal to k, okay, a certain number of choices. We just did n choose k, and we multiplied that by the probability to the k power times 1 minus p to the n minus k power. And we'll show you what that means in the example. Sometimes we write things down in math, we don't know what it means. When we do the example, we should see exactly what this means. Does anybody here know what type of blood they have? What type of blood do you have?
O positive.
O positive? It's said that 25% of people have type O blood. I think that that's one of the most common types to have. I'm not sure what type I have, but suppose that children have a 0.25 probability of having type O blood. If a family has 5 children, what is the probability that exactly 3 of them will have type O blood? We all agree that that sounds like a challenging question. And if we follow the process, we can make it pretty easy. So I'm just going to write, I like to do it this way, okay? I'm going to say, well, we're going to have type O, we're going to have type O, or type O, and then what letter should we use for the other type?
J.
J? Okay. How about N?
What?
I was just like not type O, okay? So, what is the probability of type O? What's that?
60%.
Point.
Oh, 0.25.
The probability of type O is 0.25. Everybody agree? So we're going to have 0.25 to what power?
3.
The third power. What's the probability of not having type O blood?
0.75.
0.75, and we're going to raise that to the second power. So you see that we have 5 children. So if you see right here, 3 and 2 will always add to 5. You see that? And 0.25 and 0.75 will always add to 1. And that's what this means right here. These two numbers will always add to n, and these two numbers here will always add to 1. Now, we can arrange that all sorts of different ways. So let's choose our arrangement. Our arrangement is going to be, we have 5 trials, and how many of them do we choose to be O? We choose 3. So we want to calculate 5 choose 3. What goes on the top?
5 times 4 times 3 times 2.
And what goes on the bottom? 3 times 2 times 1 times 2 times 1. Fortunately, this is really simple. We could just cross off the 3's, the 2's, and the 1's, and we get 20 on top. We get 2 on the bottom for a total of 10. So let's go ahead and model that in our calculator. Make sure you get the same thing. Sam.
So how do you, I'm not on the brain for it, but how do you, on the last part of the fraction, how do you get that piece in?
The 2 times 1?
The squared?
This guy?
Yeah, because that's how many, I don't know, how do you get that in?
So the top was 5, right?
Yeah.
And then I divide by the 3,
Yeah.
and then 5 minus 3 is 2. So those two things will always add to 5. Okay? So suppose it was 10 choose 6. There'll be 10 factorial on top. It'll be 6 factorial times 4 factorial on the bottom. Those two always add to 10. Always. Okay, let's see what you got for your calculation. Make sure we got the same thing. And then we're going to try to have you guys do a couple on your own.
And you also should be get the zero.
Is that about what everybody got?
Yeah.
Is that accurate? Okay. All right, so we're going to talk about the conditions for the binomial distribution, and I'm going to do example 4 with you, and then I want you to try to do 5 and 6 on your own. And if you can do that, we should be in good shape for Monday. If we can't do that, then Monday could be a little bit shaky. So, how do we know if something has a binomial setting? And this is important. And the first thing is and we use this acronym. We use the acronym BINS. And BINS means this. First of all, it must be binary. And what binary means is there must be a success and there must be a failure. So notice we had type O blood or we had not type O blood. We had a blue marble or not a blue marble. We have heads or we have tails. You live or you die. You have first hour, you don't have first hour. You went to McDonald's, you didn't go to McDonald's. It must be binary. There must be a success and there must be a failure. Okay? That's the first and most important piece. The second one is that the results are independent. So notice when I was grabbing a marble from the bag, what was I doing every time I grabbed that marble? I then put it back. So every time there was then, 5 more marbles in the bag, right? Like you can't take one out and then take another one out and then take another one out because then they would be connected to each other, right? So sometimes you have to look at it and say, are these independent or are they not? The next one in terms of n means that there has to be a numbered, certain numbered trials. So we have to determine ahead of time, how many marbles are we choosing? We're choosing 2. How many kids are we choosing to have type O? We're choosing 3. You have to make sure that you've chosen that certain number. And finally, the last one is S. That means same success. And the same success means every single time we go and grab, we have the same probabilities. Okay? It can't change. Every time it must be the same probabilities. And that's what BINS stands for as we work through this. And so we'll do this example right here. And then we want you guys to try the next one on your own. So again, I'll do this one, and then I'd like to help you with this one, and the last one I'd like you to do on your own. A basketball player shoots 40% from three-point range. What is the probability he makes exactly 4 of 7 shots in a game from a three-point range? So, I'm going to model this out. He's got 7 options, okay? So we're going to say, what should we use for a make? M? Okay. What should we use for a miss?
An X.
Okay, so he's got 4 makes, it says, and he's got 3 misses. X, X, X. That's what you want to do, right? So, what is the probability that he makes the shot? Says in the problem.
0.4.
0.4, good. Every time it's 0.4. So we should raise that to what power? The 4th power. What is the percent chance that he misses? 0.6. Notice again that these should always add to 1, and they do. And what power would that be to? It would be to the 3rd power. So that's the probability. I just need to now determine that coefficient out front. And so I have 7 trials, and I'm choosing how many makes? 4 makes. So I have to calculate 7, choose 4. So on the top, 7 times 6 times 4, 5, excuse me, times 4 times 3 times 2 times 1. And on the bottom, I have 4 times 3 times 2 times 1. Sam, what else do I have on the bottom?
Times 3 times 2 times 1.
Times 3 times 2 times 1. Good.
Not very nice.
Oh, Ben. I get rid of the 4 times 3 times 2 times 1. And we can do a little trick here as well. 3 times 2 is 6, so that gets rid of the 6. So what do I have left? I've got 35. So I had 6 times 7 times 5, and at the bottom I had 3 times 2 times 1. I know 3 times 2 is 6, right? So I just cross out the 6. So now I'm just left with 7 times 5 is 35. So I've got my 35 out front. I could go ahead and multiply. See if you could get the same answer as me. 35 times 0.4 raised to the 4th power times 0.6 raised to the 3rd power. He's got a 0.193 chance. Okay? I want to be clear, is it possible he could make more than 4 of those shots? Yeah. Is it possible he could make all of them? Yeah. So those would be less of a probability. We haven't added those on. That's exactly that many amount. Okay? So you roll a fair 6-sided die 6 times. What's the probability that you roll a 3 exactly 3 times? I'm going to go ahead and model part of this for you, and you're going to carry it out the rest of the way. I'm going to roll a 3, and a 3. And then I'm not going to roll a 3. I'm not going to roll a 3. I'm not going to roll a 3. What is the probability of rolling a 3 with a die? Close. How many numbers are there on a die?
6.
And 3 would be one of those options, so the odds are 1 out of 6. You go ahead, see if you can carry this the rest of the way. Go ahead. I will slowly put stuff up there to help you out, but see if you can carry it out the rest of the way.
And then you do times 2 times 1. That's not right. This one.
Yeah.
Yeah. Oh, I thought it was 2. And then you do this cross off 6. So you got 8 over 1. Yeah, it's 20. And then you plug it back in. Oh yeah. And then that. So 20. Yes. Well.
Did everybody come up with 20? Are you okay with the 1 out of 6 and the 5 out of 6? Why didn't I convert those to a decimal? They're kind of messy, aren't they? It's 0.16 repeating and then 0.83 repeating. So I'm going to leave them as fractions. You can do that on your calculator. Let's see if you got the same thing I did as I type it in. You have 20 times parentheses 1 divided by 6 raised to the 3rd power, and then times 5 divided by 6, and we're going to raise that to the 3rd power. And I get 0.053. Everybody good with that? Is that what you got? Okay, you try the last one completely on your own. I see it from beginning to the end. Go.
Hey, stop. Don't say that word.
Okay. Again, you'll be in a lot better place on Monday if we can do this type of a problem. If we can't, then Monday's gonna be hard.
It's 2 and then. So then.
A plus? There you go, Breezy. We knew you'd get it. Am I the only one that calls you Breezy, or do other people do that?
It's only you. You've asked me this before.
Okay. I sometimes forget. Sometimes my nicknames catch on.
No.
You have a good weekend.
Yes, sir.
Go get some candy tonight.
I will.
What did you get?
12 times 11?
So.
Oh, another person.
What's
Wait, I
12
think I'm
what's 12
actually
times 12? Okay, what's 11 times 11?
Does this say something?
What's 12 times 11?
Okay, so these.
For what?
So 0.
11 times 5
It
is
says
0.
0.10.
You just said
It says
11
0.10.
times 11 is 1.6.
So that's that. Then the rest of that, 39%. And then you put it to, it'll go to 1, 2, that's 1, 2. And then you put an exponent of 10, 12. And then you do this whole thing, and whatever you get, you plug it in.
Just making sure you said that stuff.
Is it 66? One last thing I'd like to show you before we go over this problem, as I have it set up here, is sometimes people wonder, well, what do you choose? Is it 12 choose 2 or is it 12 choose 10? 12 choose 2 is exactly the same as 12 choose 10. It doesn't matter how you set it up, they will be the same. Okay? You end up with the same numbers in the denominator, so it doesn't matter. See that? As I multiply it out, I've got the 66 out front. 66 times parentheses 0.1 raised to the second power times 0.9, and we're going to raise that to the 10th power. And I've got a grand total of 0.23. There's a 23% chance that the river does flood exactly twice. And that might seem contrary to you because you're like, well, 10% of the time it rains, it floods. Well, it might flood once, but it also might flood twice, 3 times, 4 times, 5 times. Wouldn't you agree that the chances if it floods 10% of the time, the chances that it floods at least once is pretty good, right? So, statistics in those numbers can be somewhat challenging. I don't have anything for you to work on right now. That will be on Monday. I will do my best to keep the assignment on the shorter side, but these are the problems you'll be trying.